this is the origin. The nodes in the right subtree are in the positive x direction, and the nodes in the left subtree are in the negative x direction, more or less, right? Here you can see, assume that this particular length, the length of this particular node and the node in and this particular right child is nothing but equal to 1. So the distance of this particular node, node number 3, is nothing but equal to what? 1. Distance of 7 is nothing but 2. Similarly, the distance of 2 is nothing but -1. The distance of 4 from the origin is nothing but -2. And if you want to calculate the distance of 5 and 6 from the origin, you can see that at this particular point, what we are doing, we are decreasing the distance by -1, correct? So here you can see that initial distance is 0. 0 minus 1 is nothing but -1. If you go into the right direction, what you are doing, you are just adding 1 to the distance. So here you can see that at this particular point, the distance is -1. If you go in the right direction, you will just add 1. So -1 plus 1 is nothing but 0. So you can see that these nodes will also lie at the origin. It will be something like this. Let's say this is 5. And here only it will be something like 6. And these nodes, if you check the horizontal distance from the origin, this is 0 and this is 0. Correct? Anyone has any doubt till here?
No, but Naveen, that 1 is already considered as a 0, and how come the 5 will be 0? It should be 1, right?
We have to consider these nodes by taking 1 as the root, that's the reference. So if you go in the left direction, what we will do, we'll just subtract the horizontal distance by -1. If you go in the right direction, then we'll just add +1. There can be multiple point which lies at the same line. You can see this is the y-axis, right? If you see the y-axis, there are so many points: 0, 0, 0, maybe let's say 1, 0, 2, 0, 3. There can be multiple, you can say that points which lie in the same line. That is possible, right?
Yes.
Here, what is varying here? The vertical distance is varying here. But what we are talking about, we are talking horizontal distance. We are not taking this vertical distance. Correct?
Yes.
So what you have to do, you have to store these horizontal distance and the node information somewhere. Maybe you can just take a hash map of integer comma, let's say node. So when you traverse this particular hash map, whenever you will traverse, you will have both values, the node value and the horizontal distance value. If you traverse the left subtree, what we will do? We will just subtract the horizontal distance by -1. If you traverse the right subtree, just increase the horizontal distance by +1. Now here you can see, we'll store this initially. What will happen? You will store the node 0, the root node with horizontal distance as 0 and the value as 1. This you will store. Then you will traverse the left subtree. You can see that then the next node, maybe you are traversing in the pre-order way. Next node is nothing but 2. Horizontal distance is -1. Node is 2. Similarly, -2, node is 4. Then you will traverse 5, but you can see that the horizontal distance already exists. So what we will do, we'll just delete this or update this value, something like this. So that depends on you whether you will print 5 or 6. Correct? Then the next value is nothing but 3 with horizontal distance as 1. Next value is nothing but 6. horizontal distance as 0. So you can decide whether you will go for 5 or 6. Both are correct. And then you will have the node 7 with horizontal distance as 2. So what we have to do, we have to print exactly one node at every horizontal distance. So if you are seeing the nodes from the bottom, what you will observe here, you will observe one node is present at horizontal distance -2, one node is present at horizontal distance -1, one node, you will see only exactly one node at horizontal distance 0, similarly at horizontal distance 1 and horizontal distance 2. Regarding the bottom view, if there are more than, you can say that one node present at a given horizontal distance, then you will take the last node which is visited. You will take that node which is visited at the last. So in this case, you will see that the 6 is visited at the last. So you will consider that only. Correct?
Okay.
So let's try to implement the same. I'll share the Eclipse screen now. Class 39. Today's date is 7th of April. Maybe we can create one class here. What we can do, we have to find the bottom view of the tree. For that, what we can do, we can take one hash map here. Maybe let's say static hash map, where we'll store the horizontal distance, comma, the node information. Here, maybe we can declare map equal to new hash map. Public static void bottom view. We can pass the tree node initial is nothing but root here, and initial horizontal distance is nothing but 0. This is the reference. So how we will traverse the node here? If you go into the left subtree, you will just write root dot left, and you will decrease the horizontal distance by -1. If you go into the right subtree, you will just write root dot right, comma, horizontal distance, whatever horizontal distance we have, and we'll add 1 here. Since we are doing the pre-ordered traversal, so there in the pre-ordered traversal, if you remember, we are printing the node first, then we are traversing the left subtree and then the right subtree. So here we are not printing anything. Instead, we are storing the information into the hash map. How we'll do the hash map? So we'll write here if map dot contains horizontal distance, if the key is there, if there is an entry already with horizontal distance, what we will do, we'll update the node value there. So we'll write here map dot put whatever horizontal distance you have, and the value is nothing but root only. Instead of storing the root, you can store the integer also. There is no harm. So here you can just put root dot data. If the value is not there, then in that case, what you can do, just put the value here. Both are same. Here we are updating it. Why we are updating? Because in bottom view, we will see the last entry. We'll see the last entry from the bottom. So we'll just write map.put horizontal distance and root.data. Obviously, we are calling the bottom view function here. So here we will write something like this. If root equal to null, then in that case, obviously there is nothing to traverse. Then in that case, we can simply return. These are the base conditions. Once we have the result, once we call this bottom view function, we'll pass the root here initially and horizontal distance as 0. Consider this particular tree where we are creating the tree. Let's take this particular tree for now. Something like this. So here you can see initially we are passing root and the reference, the horizontal distance of the root node is nothing but equal to 0. That we assume that it is at origin. And then we are deciding after this what you can do, you can just print the hash map here. How we'll print the hash map? You know very well, for map dot entry integer comma integer map dot entry set. You'll simply write system dot out dot print map dot get es dot get value. And maybe here you can just print a new line. Something like this you can do. Let's try to print it. Here you can see that it is printing 60, 20, 40, 30, and 70. Let's see whether it is correct or not, or we are missing something. What is the data here? Let's see the data. We are creating 10 here, 20, 30, 40, 50, 60, and 70. So ideally, if you see the node from the bottom, if you see the tree from the bottom, you will see 40, you will see 20. Out of these two, you will see 1, then 30 and 70. So output will be 40, 20, either 50 or 60, 30 and 70. Let's see whether it is correct or not. See here 40, 20. Okay. 60, 20, 40, 30 and 70. They might not be in the same order. If you want to use the same order, I think there is a different hash map there. Linked hash map you can use instead of hash map. That depends on you. Let's write here linked hash map so that it will maintain the order. If you do this now, then you will get the order 60. Why the order is not preserved here? Let's let's do for 40 first, right? How this order is happening? Maybe. So in that case, you have to use the tree set, not the linked hash set, because this is sorting based on the horizontal distance. Let's do now. So here you can see the output is 40, 20 out of 50 and 61, then 30 and 70. Now, if you want to print the top view here, there is only one change required. Here you can see, if you see the tree from the top, you will see the node which is presented horizontal distance -2 is nothing but 40. then 20, or maybe just I'll write something like this so that you will get more clarity. If this is the origin here, and if you see the tree from the top, you can see this is the tree. If you see from the top, you can see one node is present at horizontal distance -2, that is 40. One node is present at horizontal distance -1 is nothing but 20. One node present at horizontal distance 0. If you see from the top, you will see only 10, not 50 and 60. At horizontal distance 1 is nothing but 30. At horizontal distance 2 is nothing but 70. This is the output. So might be you have to change only few lines here in case of adding it. So whenever you will see any entry, you will add only when there is no entry for that particular horizontal distance into the hash map. Then only you will add, otherwise you will not add. So maybe if you want to print the top view also, you have to made only one small change here. Let's write top view here. Instead of this, if the key is not there, if the horizontal distance is not there, then only you will add it. Otherwise, you will not add it. If the key is there, then we will not do anything. If you follow this, then you will see the output will be something like this. Why 10 is not printed here? Okay, we are calling the bottom view. We have to call change here also, right? Sometimes we have to forget. Okay, anyways. See here 40, 20, 10, 30, and 70. Only a minor change is there in case of top view. Anyone has any doubt here?
Clear, Naveen.
In case of left view and right view, I think that you can try. Maybe give it one more try. There is nothing in the left view and right view. Maybe just assume the tree something like this, 20, maybe 30, 40, 50, and 60. If you see from here, you will see what you have to do in left view or right view. You have to print the first node in every level, more or less. So here you can see at level 0, you will see 10. Level 1, you will see 20 and 40. Out of this, the first node is 20. In level 3, you can see 30, 50, and 60. So the first node is 30 here. That's it. So more or less, I think you have to make change in the level of the traversal here. Here you can see that we are printing every node in every level, right? If you see here, this particular for loop is nothing but printing every node in every level. What we have to do? We have to print the node if it is the first node. So maybe here one small modification is required. That's it. Nothing else. That maybe you can do. So try it out. If still you have any doubt, let me know. Correct? I think these 4 questions I gave you as a homework. Anyone has any doubt till here, please let me know. Otherwise, we'll move ahead.
No, Naveen, it's clear.
Now let's discuss one concept here. Till now, if you see here, we are creating the tree like this, but it's not like that. We are manually creating the nodes, then we are one by one linking the nodes one by one and so on. It's okay for a small tree, but let's say if you have hundreds of node here, how you'll create the tree? So in that case, what generally we will do, listen carefully. There are algorithms to generate the tree if few orders are given to you. For example, here, please listen carefully. Suppose this is a given tree initially. You know this tree 10, 20, 30, 40, 50, 60, and 70. If you traverse this particular tree, you will find the pre-ordered traversal of this particular tree is nothing but equal to what? 10, 20, 40, 50, 30, 60, and 70. This is nothing but the pre-ordered traversal. If someone asks you what is the in-order traversal of this particular tree, in-order is nothing but equal to 40, 20, 50, 10, 60, 30, and 70. So here you can see these are the pre-order and in-order traversal. So what they will say, they will just give you the pre-order and in-order traversal and then say construct the binary tree from the pre-order and in-order traversal. How you will do it? If you notice one thing here, in case of pre-order traversal, the root node will be printed first. Correct? So here you can see that how we, if the pre-order and the in-order traversal are given to you, how we will identify which one is root. We can identify easily. The first data is nothing but the root node here. And in case of in-order, the root node is here. All the nodes in the left side of root node are in the left subtree, and all the nodes in the right side are in the right subtree. You can see here. Whatever data is present here in the left side, 40, 20, and 50, they will be part of the left subtree of 10. Whatever data present in the right side of 10 are part of right subtree of 10, 30, 60, and 70. So what we can do, one by one, we will traverse the pre-order and create the node. And based on that, we will assign the values. We'll do something like this. Listen carefully. Initially, let's take the pre-order traversal counter value as 0. What we can do, we can go at this particular index, create the node, and recursively we will construct the binary tree, something like this. What we can do recursively is, we'll find the index of this particular node 10 in the in-order array. Initially, the in-order index is 0, 1, 2, 3, 4, 5, 6. We will search the node 10 or data 10 from 0 to 6. You can see we find the node 10, node data 10 at third index. Then what we can do, we can recursively find the or create the left subtree and construct it here. We'll write something like, say, root dot left equal to whatever we will construct here. Then recursively we'll calculate the right subtree. How will calculate the left subtree. Left subtree will be initially the initially the index will be from 0 to 6. But here in the left subtree, you can see that the index will come from 0 to 2 only. Here the index will be from 4 to 6 only. So whenever you will search for any node, what you will do generally, you will just find the or search the node from starting index and the ending index. Once you go to that particular node, all the nodes in the left side of that particular data are part of the left subtree, and all the data in the right part are part of right subtree. That we can do recursively. So I'll write the code first, then I'll explain you in detail manner. Let's create one class here. Class 39_1. What you are given the pre-order and in order of the given tree. In case of that particular previous tree, the pre-order is something like this: 10, 20, 40, 50, 30, 60, and 70. The in order is nothing but 40, 20, 50, 10, 60, 30, and 70. This is given to you. Let's create one function here, public static void, or maybe tree node. Create binary tree. Initially, you can see we will pass the two array as is. The pre-order array and the in-order array. Will pass the starting index. Will pass the ending index. What we will do here, we can take one variable, maybe, let's say static int one variable, let's say pre order index will mark this particular value initially as 0. Here what we will do, first we will create a node here, tree node root equal to new tree node. What should be the value? The value is nothing but go to the pre-order array and go to this particular index and create the node with that particular value. Once you create the node, ideally what you will do, you will find the node in the in order array. you'll find that particular data into the in-order array. Once you got the index, you have one idea that all the data in the left side are part of the left subtree, and all the data in the right side is part of the right subtree. So you will do something like this. You'll try to search the given node from starting index to ending index. So int I equal to starting index, I less than equal to ending index, I plus plus. Let's say int index is equal to -1. If this particular node, that is nothing but root.data, equal to in order at index I, then immediately what you will do, you will just put index equal to that particular I and break from this particular loop. Once you have this particular data, you will immediately say, you will construct a tree like this. You will call the create binary tree. You know the left subtree of root is nothing but start from starting index and go till I minus 1. This is nothing but root dot left. And root dot right is nothing but equal to create binary tree. All the data in the right side is part of right subtree. That is nothing but you will just put the pre-order as is, the in order as is. Starting index will be index plus 1 and ending index. At the end, once you create the root, once the left subtree is there and the right subtree is there, then you can simply return the root here. Something like this. You can play with this value also. What is the starting and ending index? Here you can see that we are changing the starting index and ending index. So we have to do all these things only when the starting index is lesser than equal to ending index. But suppose the starting index is greater than equal to ending index, then in that case you have to simply return null here, more or less, to handle the base condition, because these two values are only changing here. Let's try to call this particular function, create binary tree, will pass the pre-order array, will pass the in-order array. The starting index is 0, ending index is nothing but in order dot length -1. What it will do, it will return us the root value. That thing, that particular node we will store something like this, root equal to this. And maybe here you can, once we have the binary tree, you can just find the post order, whatever, or post order, level order, whatever you want. Let's try to debug this particular code. Then we will see. Listen carefully. We can call the function like this. Please listen carefully. We are calling construct binary tree CBT. We are passing the in pre-order in order as is. Starting index is 0 initially. Starting index is 0, ending index is nothing but 6. What we are saying? First, go to this particular index in the pre-order array. At 0th index, you will see 10. So create a node with that particular value. Okay. Increase the pre-order index by 1. Search this particular data in the in-order array. When you will apply the linear search in the in-order array, you will see that the 10 will present at index 3. So what you are doing now, you will say root.left, whatever root you will create, that is nothing but, let's say it is created at 1k. So 1k left is nothing but equal to CBT. Starting index is 0. Ending index will be index minus 1. What is index here? Index of 10 in the in-order array is nothing but 3. 3 minus 1 is nothing but equal to 2. So we'll call here CBT 0, 2. When you call CBT 0, 2, again you can see starting index is 0, 0 is greater than equal to 2. No. You will create the root node like this. Go to the pre-order index in the pre-order array. Go to the first index, create the node. Node will be 20 now. And then find the node 20 from 0 to 2 in the in-order array. From 0 to 2, you can see that the node root data, that is 20, is present at index 1. So we'll simply say CBT, whatever root you will create, you will just write root.left equal to CBT. Starting index is 0, ending index is nothing but index minus 1. What is the index of 20 here in this? It is nothing but 1. 1 minus 1 is nothing but equal to 0. You will say CBT 0, 0. Obviously, you will increase 1 here after creating the node. Now, what you will do, you will create one node here. Node data will be data present at pre-order index in the pre-order array. Here you can see that if you go to the second index, the data is nothing but 40. You will create a node with data is 40. Okay. I think this condition we have to change. It should be starting index is greater than ending index. Then only we have to return null. In this case, 0 is greater than 0. No. Created this node with data as 40. Find the node find the data 40 in the in-order array from 0 to 0. Here you can see that 40 is present at index 0 only. So it will return index value as 0. Then we will say root.left equal to CBT. Starting index is 0, ending index will be index minus 1. Index minus 1, you can say 0 minus 1 is nothing but minus 1 here. When you call the CBT of 0, minus 1, it will be quoted in the base condition. 0 is greater than minus 1. No. 0 is greater than minus 1. Yes. It is caught in the base condition, so it will return null. So this particular node left child is nothing but equal to null. Then we will say root.right equal to CBT. Ending index, you can say that is nothing but equal to index. Starting index is index plus 1. Index plus 1 is what? 0 plus 1 is 1. Ending index is 0. When we call this 1, 0 here, what will happen? It will again quote in the base condition 1 is greater than 0. If 1 is greater than 0, what it will do? It will return null here. So right side of 40 is also null. And then we will, after creating this particular node, we are returning to the caller. Who is the caller of this? Caller of this is nothing but 20. So 20 left child is nothing but left subtree is nothing but this only. Once we create the left subtree, we'll try to call the right subtree. So root.left equal to what? root dot right equal to CBT. Here you can see that for this particular node 20, from 0 to 2, the index we got as 1. So starting index will be index plus 1, 1 plus 1 is 2. Ending index is nothing but 2 here. If you do this, what will happen? You will call this CBT of 2, 2. 2 is greater than 2, that is not true. So we'll create a node which is present at third index. Correct here. In this case, the third index value is nothing but 50. So we'll create a node with data as 50. Then you will write CBT, find the node, find the root data in the in order array. 50 is present at index 2. So here you can see that CBT starting index will be starting index only, ending index will be index minus 1. So 50 is present at index 2, 2 minus 1 is nothing but 1. When you call this particular one, you will say starting index is greater than ending index. So the left side of this particular is also null. Similarly, when you call the right side is nothing but index plus 1. Index is here 2 here. 50 index is 2, 2 plus 1 is 3. And here we will pass the ending index is 2 here, 3 is greater than 2. It will also return null here. Once it will return null, we will return the root node to the caller. This is the caller here. The right child is nothing but this particular node once we get this. Similarly, once this particular call is over, it will return the root node to the caller. Who is the caller of this? This is the caller. So this you can see that for 10, the left subtree is something like this. And then we will again do the same thing. For this you will say, we will find the right child of root node. What is the right child of root node? Here you can see root dot right equal to CBT. 10 is present at index 0. Ten is present at index 0 in the pre-order array. We have to find out in the in-order array. So it is present at index 3. We have to find out what is the index. Index is 3. Here, when we call the right subtree, we will pass index plus 1. 3 plus 1 is 4. Ending value is 6. So similarly, when we call CBT of 4, 6, we'll go to the fourth index. Fourth index, you will see 30 is the node. You will create the node here. Then find the left subtree and right subtree. The left subtree of 30 is nothing but you can say 30 is present at index 5. So we'll call here CBT. Starting index will be 4. Ending index is nothing but 5 minus 1 is 4. So we'll call CBT of 4, 4. Starting index is not greater than ending index. You will create one node here. Obviously, we'll increase the pre-order index every time by 1. We'll go to the fifth index. The element found is nothing but 60. We'll create one node here with 60 data. Then we'll find out the left subtree of 60. Here you can see that starting index of this is nothing but 4. You will see 60 is present here at index 4 location. So ending index will be 4 minus 1. That is nothing but 3. When you call this 4, 3, it will quote in the if condition. It will return null. So the left side here is also null and the right side here is also null. When you call CBT, right side is nothing but 4 plus 1 is 5. And ending index is 4. 5 is greater than 4. It will again hit into this condition. Once you create this particular node, it will return to the caller. So here you can see that this is nothing but the left subtree of 30. Similarly, you will increase this index, create the right subtree of 30. So we'll call here 30 is present at index 5. When you call the right subtree, we'll pass index plus 1 value. 5 plus 1 is nothing but 6. Ending index is 6. When you call this 6 comma 6, what will happen? Obviously, you will create one node here with this particular data. Data here is nothing but 70. Then you will write here for 6 comma 6. For 6 comma 6, the 70 is present at index 6 in the pre-order array. When you find out the left subtree, starting index is 6, ending index is 6 minus 1 is 5. When you pass this, you will say 6 is greater than 5. It will again hit into the if condition and it will return null. That is the left side of 70 is null. And when you hit the right subtree of 70, you will see will pass the index plus value, that is nothing but 7 here, and will pass the ending index, that is 6 here. 7 is greater than 6. You will see the right child of 70 is also null. Once you do this, you will return the node to the caller. Who is the caller of 6 comma 6? This is the caller. That is nothing but node number 30. So you will just connect this particular node. Once these left subtree and right subtree are ready for node number 30, you will return the root node to the caller. You will return to this particular caller. And once this particular node is over, you will return to the root node. And here you can see that once we assign this particular to the root node, what will happen? You will have the root node here, more or less. And once you have the root node, you can easily find the post or the traversal or whatever you want. Correct? So maybe here, in case of post or a traversal, let's call this particular function. You will print the post or the traversal and pass the root node here. Once you have the root node, if you run the program again, you will see this will get printed. This is nothing but the post or the traversal of this particular node. You will see here. This is the post or the traversal of this particular tree. If we are not doing any mistake, let's see whether everything is correct or not. This is not correct, right? What we are printing here? Okay, we have to print the left subtree first in case of this. Here we have to print the right subtree. So if we do this, here also we have to print the left subtree first, right and data. 40, 50, 20, 60, 70, 30, and 10. So this is how we can create or construct the binary tree, more or less. You'll see the recursive function here. If anyone has any doubt in this particular function, please ask me. If you try to think or try to solve any question of binary tree, try to think in terms of recursion, then I think things will be little easy. If you think in iterative manner, then it will be very difficult to write the complete code. Anyone has any doubt? If you see here, if you see the time complexity here, more or less what we are doing, we are creating the node here, then finding out the index, and then traversing the left subtree and right subtree. So this is nothing but, if you see these three lines, these three lines are nothing but pre-order traversal. What extra thing we are doing here is nothing but this only. That is nothing but finding the index of the given node in the in-order array. And here you can see we are using linear order traversal. So at worst case, in worst case, how it will take around order of n square time complexity to create the binary tree. Why? Because we are using linear traversal here. We are using linear traversal here. Something wrong with my system. Okay. Anyways. So here, if you see what is the time complexity is nothing but order of n square. Why order of n square? Because we are searching the data here linearly in the in-order array. And searching linear traversal in an order array is nothing but order of n times. So it will take order of n square time complexity to construct the given binary tree from pre-order and in-order array. I will share the assignment question with you. In that particular assignment question, what you have to do, you are given the post-order traversal and the in-order traversal of the given tree. Correct? What you have to do, you have to find out the pre-order traversal of the given tree using post-order and in-order tree.
Okay.
This is one question. I don't know, this particular dashboard is not working. Otherwise, I will write here. Let me just try again. If it works, something is wrong here. Let me just again try. Sometimes these machine are got hanged up or I don't know what. Maybe there is some issue. I don't know what is the issue, but not able to connect actually. So I will say not an issue. This is first question that you have to try. You are given the post-order traversal of the tree and in-order traversal of the tree. And then you have to find out the pre-order traversal. The second question is, in this case, while constructing the tree, it is taking order of n square time. Why? Because we are traversing it linearly. Can we optimize the code? Can we create the binary tree in less than order of n square time when the pre-order and in-order traversal are given to you? This is the second question that you have to do. I hope both questions are clear, right?
Yes.
I'll share the photo of these two assignment questions once my system is working, right?
Okay, sir, no problem.
Some issue. Let me fix it and then I will share. Not an issue. I'll share the code with you in the meanwhile.
Okay.
You will get the code by tomorrow morning from the management in your respective groups. And your assignment questions as well. So we created, I think, 2 classes, 39 and 39_1. You will get both the codes, correct? try to practice as much as questions as possible, because here we are heavily using the recursion as well as other concept also. You can see today we see how we can use the hash map in the tree. And I think 2 days back in the last class, we saw how we can use the queue and the stack in the tree class, correct? So that's why whenever you will give an interview, there are high chances that you will get questions from tree data structure, because in this, I think more or less every data structure will be used here. Correct? You can use every data structure here, array,
Yes.
stack, queue, string, hash map, and all. We can use every, and here you can see we are heavily using the recursion also. If you know the recursion, then I think you will know most of the concept of DSA. So try to practice the questions one by one, and let me know if you face any difficulty. Thanks everyone for joining the class on time. I will save the assignment questions once my system is working.
Yeah, okay, sir.
Thanks everyone. Bye. Good night.
Good night.
Yeah, bye, Naveen.
Bye. Good night.